diving into the content we have today, I'll have everyone introduce themselves and tell you a little about their organization. So let's start. Clark from Crank Software. Over to you.
I'm the VP of Sales and Software, but I'm also one of the co-founders. Crank Software, we are a U.S. solutions, and we provide tools and services to get easier and faster for us and engineers to bring graphical products to market for the embedded devices.
Wonderful. And Stephen?
Hello, I'm Olson. I'm the North American manager at QNX, coming 2 years of service with them. I've been in the real-time system space for over 25 years, specifically on safety-level software.
Thanks, Stephen. And Daniel?
Hi, my name is Lang, Chief Marketing Officer Toradex. I'm in the industry for more than 3 years. Toradex is focusing on of use and embedded compute in areas such as medical, industrial automation, smart city measurement.
Wonderful. Thank you. And finally, Chris Rommel, BC Research. Can you introduce yourself and jump right into the...
Great. Thanks a lot. Appreciate it. So this is Chris from VDC. I'm a vice president who leads the IoT and MB research company, and we're a market research firm from the global community and been looking at that for over 20 years. Today, I'm going to be sharing some results and insight research, which I captured input from over 700 practitioners and insight into some of the business and technical trends in engineering organizations with a specific focus on some of the trends impact the medical device marketplace. So to probably horizon of view, the medical industry is at a time of unprecedented with new device investments reshaping device functionality needs. And one clear trend we see really manifesting is the explosion of GUIs in medical device. And with the user really operating environment experience now a sort of production, ways to address this element has become a critical need to accelerate overall system and ultimately product in the marketplace. And while I certainly see a very high growth rate of the integration of looking at my research, one thing that really see was that only 35 of the users with a design reported use a design tool specifically focused that layer. When you think about pain in development, and especially as intuitively with end product differentiation, this is clearly a more OEMs need to address, and more specific, all the other challenges development need to address. It is for OEM sections geared at that layer up as they plan their device software stack. So device failure is never an option, especially when you're safety critical. So we shouldn't accept project execution either. So some taken this dynamic and that put for granted. So while the whole has really long some deadlines, schedule is far worse medical device development. As you can see here on this chart, 10% projects were completed behind schedule. Scenario where the status quo device and new platforms accelerate product development. So seeing the results in the medical sector that were certain worse than the embedded in whole, I wanted to peel a bit on the problem and try to figure out how we as an can address common challenges that we're seeing, at least from a schedule perspective. And when we asked about the reasons, engineers willingly reported a common theme their responses, and that accelerating rate of change in goals and complexity. And with that theme, you can see that internal development resources are simply stressed for these organizations to keep up. And in today's, it's not likely that there's going to be a story of reinforcement coming, racing in to give you more to throw at a challenge line. And for many projects in the medical sector, they're on the safety critical considerations. Many of these devices which really only work out some of the challenges organizations face. The noted difficulties managed and the deleterious it is having on project performance we just looked at, critical to find ways to elements of the materials and stack. In essence, OEMs must set common technology foundations when they're making their design decisions to help accelerate their development and hopefully in the future too maximize IP reuse. So on this next slide, I wanted to show how this is and really can change to align with these goals. Already, the long fragmented embedded market has been consolidating around a smaller set of technology choices in the ecosystem. And certainly while it's still quite diverse in the grand scheme of things, more and more OEMs are seeing the need to choose third-party technology. And the transition to third-party operating systems is long underway in the industry. And here's a snapshot of what that embedded operating system looked like a dozen years ago in research. And as you can see there, many organizations at that point were still developing their own operating systems. Still more, were developing devices and maybe had no formal system on their product at all. But evolution of system requirements changed everything, and OEMs were looking to add more and more smart functionality to their systems. They recognized the need for sophisticated OS platforms, and in some cases, again, that meant adding one altogether. And others, that meant moving to a third-party solution when they couldn't scale their own internal efforts. And then the desire to refocus some of those resources on other stack layers and tap into what that third-party ecosystem could offer. And we saw a similar pattern in the processor landscape as well. And that's, again, an area that has been defragmenting over the years. And a great example of this, if you look at the change in the processor landscape over that same time period I mentioned on the OS side. And it's really more or less turned into a two-horse race between ARM and x86. And you can see ARM has really actually doubled its share as a percentage of respondents in a kind of a similar survey from, again, a dozen years ago, with a lot of the changes being driven by some of the investment ARM has made, I guess, from top to bottom, from M through A in its processor IP catalog. Intel has also expanded its reach with other higher performance solutions. And what really, I guess, if you look at those individually, started as individual trends, have now emerged as a coordinated, in some cases, portfolio management strategy that organizations can pursue when they think about the different elements to plan around for their next generation products. And ultimately, these changes in standardization have helped engineering organizations balance some of those goals for more capabilities while enhancing flexibility for future designs. Enhancing flexibility for future designs as they look to be able to leverage some of those available building blocks and develop more transferable portfolio IP for the future. So we've already talked about how technology use is changing, and certainly underpinning that, technology selection is evolving. Already we've seen medical device OEMs redefine the ways that they are selecting some of those building blocks for their products. And a perfect example of this has been the way that people are now selecting their hardware. If you look at the list of the most important characteristics, you can see that software availability and compatibility as the #1 hardware selection criterion. And so now we're in a position where those tight integrations and cross-domain expertise from hardware to software are becoming the industry's expectation, if not already today, the expectation of those market leaders. It's certainly something the industry at large will expect going forward. And it's really clear that feeds and speeds are no longer the deciding factor when selecting hardware. You need to think about so much more. You really want and need an ecosystem of easily integratable solutions to help you accelerate development and address some of these other bigger picture challenges you have to navigate when bringing medical devices to market. So just to summarize a few key takeaways before I hand the microphone away. In the medical device industry, the combination of new GUIs, functionality, and safety needs are driving a need for change in the ecosystem. And it's clear that the issues and goals in the embedded engineering space today are forcing OEMs to adapt. And we're beginning to see that in some of our research as well. And more than ever, OEMs need to look for new third-party technologies to help them accelerate their time to market and enable them to focus where they need to enable the differentiation. And ultimately, we see the adoption of more standard technology platforms as a way to enable that end goal. And our research supports this, with the industry moving more towards third-party platforms, as I highlighted, and prioritizing the selection of integrated hardware and software stacks. And so with that, I'll hand that back to you, Dawn, so we can learn more about how Crank, QNX, and Toradex can help organizations find platforms to help them accelerate development.
Great. Thanks, Chris. Appreciate all those insights. It's a perfect setup for the advice that our panelists will be sharing today. So I'll pass it over to Daniel Lang from Toradex to discuss some important hardware considerations.
Thanks a lot. So from Chris, we learned how important it is to select hardware and software together. Today, we show you how BlackBerry, Crank, and Toradex work together to simplify the development of a great user experiences for critical medical devices. I will start with covering the hardware. We will look a little closer at the findings we saw before and talk about possible solutions. So Chris showed the main reasons for delays in development of medical devices. So here very high up, technical obstacle, unrealistic schedule, complexity, the lack of human resources, and the hardware not available. All this calls for a simplification of the hardware design. An excellent way to achieve this without sacrificing flexibility is the use of system-on-modules. They abstract the complexity of common hardware elements such as the processing, high-speed DDRM, power management, flash memory, wireless connectivity, and more. Also, most of the software dependencies are encapsulated on the module. So you can profit of the work other people already did to support software on these modules. System-on-modules are typically a good solution if you have projects with volumes from a few hundred to a few 10,000 pieces per year. The module still allows you to build a customized board with your peripheral and your differentiating technology, but it lowers the project risk and the time to market significantly. Now take a look at the reason number 1 and number 3, change of requirements and specification. Some system-on-modules also provide advantages here. For example, Toradex offers 3 families of modules. Within these families, the modules are pin compatible. So if you suddenly need more performance, a neural network accelerator, ECC protected RAM, this can be done without a complete redesign. Just make sure when you look at vendors, you check how pin compatible the products really are, also considering the software. Now move on to the important criteria in selection of hardware. Not surprisingly, as Chris showed, it's actually software. This is the most important part when selecting hardware. We at Toradex understand this. Even we are selling hardware, and I covered today the hardware part in this presentation, almost 90% of our engineering goes into software. However, we recognize not even this covers all the customer's needs, and we put dedicated resources to create a valuable software ecosystem with our partner. For example, we work closely with BlackBerry and Crank. These partnerships allows us to solve issues and optimize the user experience behind the curtain, so to simplify the device development and maintenance for our customers. Long product availability is essential in medical products, as the life cycles are typically much longer than in other verticals. If you select a hardware provider, make sure it has a proven track record. Now, ruggedization and product durability. This is crucial, especially for critical application, as safety can directly depend on it. This is a strong focus for Toradex. We get common the question why our products are a little bit more expensive than some of the popular maker boards. And a lot of the reasons are basically on this topic. We are using industrial and automotive grade components. They are designed for a much longer lifetime than commercial qualified chips. Here, for example, on the slide, you can see that commercial products are typically qualified for 5 years, but only running 50% of the time. And then on the other extreme, industrial products, which is the majority we use, is designed to run for 10 years, 24/7, and also with a higher temperature. Some of our modules with the i.MX8 CODMAX or the i.MX8X, that's a application processor from NXP. They also feature error correcting memory, which increases the reliability and makes it easier to comply with functional safety standard. These SoCs are also manufactured in a 28 nanometer FDSOI process, which creates a more chip which is more resilient to bit flips. If your product needs ruggedization, it's a good idea to check with the hardware vendor if they do any vibration testing or other tests, showing that they can withstand that abuse. I think security is also a very important part in this topic. And here you can check if the hardware comes with any integrated security feature to support the software security features. Now, a little bit of change. On the next slide, I'd like to discuss some hardware design principles for safety-critical devices. Toradex has many customer building devices, and here some of the points how they can achieve the required safety while keeping development efforts in check. A very common way to tackle this problem is partitioning the system to keep the safety-critical parts from the non-critical parts apart. If you can do this, it's easier to certify the part which is not safety critical, it's easier to develop, and there is a higher chance you can reuse components you develop. So here, an overly simplified example of the most common approach we see. The safety critical part here on top is done with a dedicated microcontroller, often featuring lockstep. Lockstep means the code is executed twice and compared. The SOM in this schematics, the system on module, takes care of the connectivity. It provides a beautiful user interface and, for example, manage the storage. But make no mistakes, even in these use cases, it's important that the OS running on the system on module is secure, especially if your device is connected. On the next slide here, a very similar approach. But now the microcontroller is not externally, it's on the same die as the main processor. And here you can see the block diagram of the NXP IMX8 Quad Max, who has two of this microcontroller there on the same die. This concept is gaining popularity in the last year. It allows for more flexibility and also new use cases. For example, on IMX8 and Quad, you can do a CRC check on the frame buffer, so you can actually check your user interface and interrupt if there is anything goes wrong. There is also a domain controller to make sure these different CPU cores cannot interfere with each other. Then another way of partitioning the system is virtualization and hypervisor. To split the main CPU cores in different partitions, even allowing to run many different operating systems as shown here. This seems to gain quite some traction in the automotive industry. We see not very common yet, but we definitely see increased interest in that. And also on the IMX8 SoCs, they have special hardware features to support this use case. Now talking about QNX. All in these cases, a safe and secure OS is very important, and it's also not always possible to really partition it. And QNX really provides advantage if you can do provisioning, or if it's the only OS you have to run. If you like to learn more about QNX on Toradex module, please visit our website. We have a one-click installation option for many of our modules, so it's very easy for you to try that out. Now, Stephen will explain you a little bit more what to look for when selecting the operating system layer.
All right, thank you, Daniel, for that. We're going to jump into the real-time operating system, and it's really about finding the right balance. When you look at a system that needs to run, there's the operating system functionality, but there's also all your applications. And then there's the needs of both safety and security. And right in the middle, you see that balance. That's where you need to balance those needs between all three of these domains, making sure that you've got the right mix of both hardware and software, and in terms of what your complete product needs to look like. Now let's dive into safety. The first is the foundational software. This would be your real-time operating system, that you choose one that's safe. That includes the tools that you'll use, that anything that touches the code that runs on the target, your compilers, your linkers, any code generators. And libraries of functionality. So even if there's a third-party library, you want to be able to bring those in and at least assess and understand what the restrictions or requirements are from the safety use case. And then you look towards the certification standards that the system software has gone through. And I've mentioned some here. And there's also the IEC 62304 for medical. So making sure that you've got software that's gone through that is going to give you a good safety basis. And then use the safety constructs from the OS. A lot of these operating systems, and certainly QNX, comes with a safety manual that will show you how to use the product safely. And this includes deploying things like semaphores, mutexes, message passing. And you may be wondering why this picture on the right here. That's a train semaphore, and that's where that original word comes from. When trains they drill through mountains or trestles across ravines, they would only have a single track. Well, how do they share trains going in both directions so that they're not using that single resource at that time? And they would have a signal like this on either side. The trains could try and acquire that at the same time, and one of them would be granted access to the bridge or to the tunnel. The other one would have to wait on a siding until it's passed. That same construct is used in software, and making sure that you eliminate any race conditions from your software by using things like semaphores. And then, of course, protecting code by separating your code into both your code segments and your data segments, and then protecting those from each other. Now, you may have heard the term FUSA, or functional safety. That's a very important concept, and it has to do with what ifs. What if the software, or what if a hardware sensor goes out? How do we mitigate those risks in the system? So you might have something that's mission critical that if it fails is catastrophic, but you can put in a monitor that's monitoring, saying, are the results coming back from this sensor correct? Or are there pieces that maybe the communication lines have gone down? We can go to a safe state. And then there's some other things that we might be able to do in order to recover. But that's the ability for the system to essentially either repair itself or be able to act accordingly in a safe mode, not just proceed along with its functionality. And I want to compare two OSs. There are two described here. You have the one on the left is QNX. It's got the microkernel there in the center. On the right-hand side is the monolithic kernel. You can think of something like Linux in this space, but anything where you're combined all the drivers, any of the kernel modules, all those pieces get compiled together. There's no restrictions in between them. The blue wheel on the outside is about the same between them because there are protections for the applications, but that's really one of the key differences. If you look at that first line below, spatial separation, being able to separate out almost everything, and QNX does that, where almost every feature of the OS is outside the kernel. It's a very small microkernel that does some very specific things, and that allows you to achieve some of the safety that you need to in the system. And with message passing, having the ability to pass messages between these in a safe and efficient model, and those words there's a balance there as well. The safest method is to just do a message pass where you'll pass a message and there's a copy into the new data space. But that's not necessarily the most efficient. And certainly if you have a high bandwidth sensor, maybe you need to establish a shared memory region between two applications. You can do that, but make sure it's bounded and it's built into your safety case so that that buffer can be shared between them in a safe manner. And only those two applications. So it really matters in terms of how you want to put those together. Now, the service recovery, this is one that's really a differentiator. If you think about if a device driver failed in the systems in operation, that could be catastrophic for the system on the right, where you've got a kernel panic and it goes down. Well, with QNX, we can detect the failure, we can assess it, and with our high availability manager, deconstruct that driver, reconstruct a new driver in its place, bring it up to the state it was in much more quickly than you can in other operating systems. So that can mitigate any downtime that might be happening while the system is in operation. Now we'll move to security. We need to look at the needs of security in the system as well, because you have to ask the question, can the system be compromised, and what happens if it is, and what are the attack surfaces? Well, there's a lot of things that are going on in terms of denial of service, repurposing the device, access to the actual data that's on there that might violate HIPAA compliance, and then even heard of cases where access is blocked until ransom is paid. We need to make sure that we minimize that attack surface. And QNX does this as a series of gates, if you will, or spheres in this diagram. You could think of them as the Russian stacking dolls, where you could get through one, but then there's the next level and the next level. And you don't have to put all these walls up, but these are the ones that are available. That core is on trusted hardware, so establishing the root of trust from that very first line of code that gets run, authenticating the actual SOM module or the SOC, the board that it's running on, to say this is one that's valid to run on. And then looking at tamper protection, minimizing access to things that don't need to get access to do different things in the software itself. So using the MMU to its full capability, both from a data segment as well as from a hardware perspective, being able to protect that. Looking at application security. Now, this is where you think about a motor controller. The motor controller itself does not need access to the network. Other applications do, so you can actually lock down certain applications to say it can talk to these things. Maybe it needs to get to the file system to a set of parameters that it was used to tune the motor controller, and that's fine because that's what it needs access to, but we're not going to allow access to the internet directly. So things like that. And then ensuring the temporal and spatial control. The operating system is going to do that as part of its course, but making sure that you've minimized access and you don't allow a system to just run away with the processor, either in taking as much memory as it wants or taking as much time as it wants. That could have an adverse effect on the system. And then ensuring that the runtime is actually doing its job all the time. So yes, you can check periodically to ensure that the load has not been tampered with and everything is running as you would expect it to. This really comes down to the safety and security use case. And that first one, developed with safety and security in mind. This is not something to bolt on at the end. It's not like you get a padlock after you've bought this storage shed and then you put a padlock on it. It's actually designed in from the front that you should be looking at safety, using a safety manual that's showing you how to design that software along with security, and then doing full requirements testability from the beginning. A lot of people try and throw these things in at the end, and then, of course, when the schedules are late, then you actually see where, well, do we need to test it all? Can we get away with this testing? How about if we shortchange this one? Oh, we changed this feature. Do we really need to retest everything? And the answer is if you do it from the beginning, then your system is always tested to the level that you've tested it at, and each component is tested along the way. So ensure that you do that. And then ensure that you've designed it with the specific goals in mind. You're not just throwing a bunch of different software out there, but you've got that specificity in there and you're designing to those requirements. You're not getting untested code into your product. And then, of course, the security. You lock down the code in the unit that it's meant to execute on. You don't allow applications to access parts of the OS that it's not allowed to. So designing with those things in mind. Now, talked about a few things here. Really, it's about choosing the right hardware for your product in your portfolio. Maybe you have several different products. You want to ensure that you've got that right mix. and then match the hardware with the system software from a safety perspective, from a security perspective, and a functionality perspective. And then leverage the applications across the entire product portfolio. If you have a low-end unit and you have a high-end unit, being able to leverage that across your portfolio of products. All right. Well, with that, I think it's time to turn it over to Jason Clark for the user interface considerations. Jason?
Awesome. Thanks there, Stephen. So I am Jason Clark, as I said earlier, from Crank Software. And so as you could probably figure out that we're moving up the stack from the hardware to the OS to the user interface. So I'm going to talk about how we make your UIs look great and how to do that in the medical world. We're seeing a lot of evolution in the medical world. So as Chris said earlier from BDC, a lot of people are looking at adding touchscreens to their devices, and nowadays it's becoming much more expected. And the problem that everybody experiences as soon as they put a touchscreen on their device, they slowly realize the expectation is that it feels like their cell phone, no matter what the hardware I choose to use or however I come to that. So there's a high expectation for a user interface. Anytime a user touches glass, they're expecting to be able to scroll, some animation feedback, a lot of these different pieces. In the medical field, at the same time, we're seeing, because they're getting these touchscreens, there's an increased functionality and complexity that's coming into these devices, which means multiple menu layers, multiple devices that may have only been single-purpose before are now multi-purpose. And then beyond that, the medical device world is being able to be used by multiple users. So it's no longer just trained technicians using these devices. Now they're actually going to the homes, telehealth, and then you're getting to wearables and all different devices. So there's a much broader user base that's touching them that has to be able to use them. So the usability and the user experience is really high as far as getting, brand approval and also being able to use this device safely, because underneath all of this expectation is what Stephen, Daniel, and then we're talking to down below is the safety and reliability of the system is always of the utmost importance. So this is just an interesting data set I found, and I've heard about it for a long time, but it's from 2015. But it talks about how much the UI, so coming from a company that sells user interface tools and stuff like that, I understand in medical devices, we are not the primary usage of the device. It's a ventilator, it's a blood test, it's whatever it might be. There's a primary focus that's beyond us. It's not just a touchscreen for people to play games on. But what this test was, it said I don't know if it has all the numbers there, but I put the link up for it. 900 software recalls in medical devices happened between 2012 and 2015, and 423 of them were related to the user interface. So that means that much of the user interface was causing issues. So now those were tons of different issues, whether it could be input issues, usability issues, bad feedback, but a lot of that has to do with testing and how you get it to market. So in the earlier pictures, I showed you some pictures, and this is a customer of ours who just did a press release with us, and I have a couple quotes here from them. And it's Ventec Life Systems. So Ventec is exactly what I'm talking about when I say they're adding multiple functionality. They have created a ventilator system, but they've taken 5 different pieces of a ventilator that are in that same world and brought them together in a single device that's portable and usable by the end user. So in this quote, they're talking about how they brought 5 different things together, but they needed to make sure that it had the usability of a cell phone, and that's just what everybody's experiencing today. Because that usability and everything it's your product acceptance, it's how people interface with it, their enjoyment, how they like using it. So it's an important part of the entire system and how it all comes together. So Crank Software, we've been doing this for a long time across multiple markets. So industrial, medical, home appliances, automotive, and at the same time, the medical problems are what everybody's experienced. They're getting their designs from design teams, marketing teams. They need to bring them together. They need to test and validate them. Medical has this extra area where they need to make sure that, even deeper level of safety and reliability. Not that these other products don't, because it'll affect their end usability and their end performance in the market. But, and when medical stuff's at stake and lives are at stake, it's even higher of importance inside of there. So we've been doing this for a long time through our tools and through our services. So our tool that we push to as our flagship product is Storyboard, and it's an embedded GUI design and development tool. And this makes it a lot easier for people to bring in graphical assets, work back and forth with their design teams. But it's so much is about speed and ease of use, because we need to make sure that we can satisfy both the design team and an engineering team, just because the makeup of the engineering team and design teams have changed. It used to be when a lot of these devices came out, the engineering team made all the decisions. The look was very much like an old Windows dialog box, and then it just went forward. Well, today everybody wants to make sure they have their branding, their look, their feel, and even though things like, you may not think animations and everything are important in a medical UI, they are very important at a small level, maybe not large animations, but just user feedback animations that make it easier to use. So the main ways we help is by accelerating the development, helping you deal with iterations, and just giving you the flexibility by managing and making it easy to use partners like Toradex and QNX and working right off the shelf with these guys. So accelerating development is an important thing for us. So we have to do a lot of this because, as I said, the designs are coming from design teams. There's usability people involved, project management. There's a lot of people with playing into this, so we need to be able to work with them a lot better. So one of the ways we do that is by making sure we can take the graphical assets and bring them directly in and manage them back and forth. So we pull in Photoshop file, we call it Green Sketch. We also do animations on an animation timeline, and everything's at a high level that, yes, our engineers can understand, but if you ever needed your designer to step in and actually help you with the animation timeline or such, they can actually work with it, because we've done a lot of work making sure the look and feel is exactly what they handed off. So for example, if they gave you a Photoshop file with a whole hierarchy of screens and layers and naming, that is the exact hierarchy that we use inside of our system. The animations call the exact same pieces. It looks much like you would in most of the animation tools that they're used to. And you can tween those and get the exact piece. And this is an area where I was saying before, in the medical world, you wouldn't think that, animations are this important part because they want direct feedback. But when a user's going through usability pieces and getting stuff, them understanding and seeing how it works, a lot of these animations aren't so much to wow the eye and just be candy. A lot of times they're providing feedback. So instead of an up and down image, as you hit a button, you touch a button and it's a little pop of an animation. That's the kind of stuff. And you see that on your cell phone. So immediately the user feels like it's just like their cell phone. It gives them a rich feedback feeling. But what people slowly learned is when somebody's finger's on top of an image and when they release it, they don't actually always know that they pressed the button, where an animation gets a little bit of feedback after your finger's pulled away. So some of these things do make a better usability experience right out of the box just by actually involving them, making things slide out and understanding where you're going next and how you're going to use it. So it's a very powerful thing that we do, but it's a lot of it is making sure that you can take a design and move to hardware as fast as possible. Because the faster you get to hardware, the faster you start seeing your solution there. And which leads me to my next piece is, as soon as you get to hardware, that's when the feedback loop starts. In every market, user feedback's important. Your team's feedback, expert feedback's important. Medical is no different. You need feedback if you're making a device for doctors. You want to get in front of them as early as possible to get their feedback. Make sure the usability is exactly where you need it to be. So many times when people are writing a lot of code to make the user interface, it's very hard to make changes. It's very hard to do things quickly. Many times, the engineering team goes away and nobody actually sees the UI for a long period of time till it's getting close to release when they can actually start using it and giving feedback. But by then, so much time and effort's been put into making that iteration becomes really hard. And what we've learned is that the UI always changes. There's always something that needs to be evolved and such. So we've done a lot of work on making sure that when that happens, we're ready to deal with it. So a lot of that is realizing that when the change happens, it's going to go back to the design team and they're going to provide the changes back. So we did tons of work on making sure that when those changes come back from Photoshop, Sketch, or other tools that we can actually re-import them and do a merge and compare right directly. So within minutes, you can actually update your UI with a new Photoshop file and take in the new imagery, the new positions, if there's new assets, to bring them in and start leveraging them right away without breaking the entire world. And this makes it so much faster to do feedback, iterate through different changes. Being able to do a graphical compare and merge when you check into your code base is very powerful because, looking at a pile of lines of codes that have changed on a commit doesn't always tell you what that really meant to the user interface, where we actually do a graphical compare where you can actually see full images of your device as they're going in. And this makes it very easy for people to deal with this. So as the medical devices, as I said, there's so many of those pieces of earlier that there were so many errors that caused by the UI. So much of that is due to a lack of testing, a lack of user feedback, and sometimes it's because they just didn't have time to do it properly, where we really try and make sure that it's easy to get things onto the hardware fast, have an architecture that makes that easy, that when iterations do come in, and they will, that we can deal with it. So as feedback comes in, it's easy to manage. And then, so Vantech was talking about, this is one of the quotes that came out of them. We continue to rely on Crank software because it's so easy to update our user interfaces. We're constantly innovating, and Storyboard lets us tweak the graphics and optimize the animations with great ease, with minimal impact on our product development cycles. So it really gets into the speed that they can do this. And the faster you get your UI in place, the more time you have to collect user feedback as the rest of the device comes in, as the hardware is being built, the backend systems are coming in. But if you get your user interface up early and far ahead of it, and you're architected in a way that you can leverage this, you can really take advantage of a lot of these pieces. So that's all I wanted to talk to you guys about today. But, so big thing is get to target quick, see it on the device. There's so much feedback that comes back immediately. Even just seeing the performance, whether, I know as Daniel talked about, if the performance isn't strong enough, you can actually update the processor if you had a SOM module piece, making sure the architecture is correct, as it comes down to QNX, and understanding that your UI is going to evolve. So think about how are you going to handle that when those decisions come in, because the user feedback is so important in making sure that you have a great experience for your customers when they start using your stuff. And, if you wanted to try it, I should just mention we do have a free trial, and our free trial supports the Toradex boards and the QNX hardware right out of the box.